Don't worry. Yeah, you can worry.
Ya, si quiere puede leer algo para ver como el tono y el...
Aristotelian diagrams as logic.
Ahí está muy bajito. No se oye tanto. Tal vez más cerca del micrófono.
Aristotelian diagrams as logic.
Sí, está más o menos.
Logic diagrams.
No es así mal, ¿eh? O sea, porque depende cómo hacerlo.
Tal vez leer algo.
Microphone no está funcionando. ¿Sí? ¿Funciona? No está funcionando.
All things have been named like and like.
Sí. No.
No. This one is working.
But then for the question,
You have to turn it on. Yeah. It's on.
no, it's okay.
Yeah, you're ready?
Okay, so we have the second book for this morning by Stef Frijers from the University of Leuven. This is where we organized the previous edition of this event. And so we are glad that you are here. And talk today is Aristotelian diagrams as logic diagrams.
Thank you. Thanks for having me. Now, can everybody hear me? In the back? Oh, I think it's on. Wow. Wait. Because I think the people in the back from I think they're tilted over the microphone.
Yeah, I should lean forward.
Yeah.
If that's possible.
Yeah.
Oh, yeah?
Does this work?
Yeah.
Yeah,
Alright.
it's better.
So thanks very much for having me. I'm indeed going to be talking about Aristotelian diagrams and logic diagrams. Let me first do a little bit of bookkeeping. So the talk today is based on joint work with one of our PhD students, Adnan Emos. And Adnan is interested in the question, why are Aristotelian diagrams, such as the square of opposition, so common? So why do we see them all over the literature, in historical work, in introductory textbooks, in research papers? Why is that? And I will come back to this question at the end of the talk. The talk is based on a paper that's forthcoming. It will be published in the proceedings of the Diagrams Conference. It's also called Aristotelian Diagrams as Logic Diagrams. And I just saw this morning that the paper has been published now. So if you're interested, you can look it up. All right, so much for bookkeeping. So I'll be talking about Aristotelian diagrams as logic diagrams. So the first section of the talk is going to be Aristotelian diagrams and logic diagrams. What are those two things and how do they relate according to the literature? For me, Aristotelian diagrams are diagrams that depict Aristotelian relations. So the Aristotelian relations are contradictoriness, contrariety, subcontrariety, and subordination. What do I mean? Well, two formulas are contradictory if and only if they cannot be true together and they cannot be false together. They are contrary if and only if they cannot be true together, they can be false together. Subcontrary if and only if they cannot be false together but can be true together. And finally, in subalternation, if the first formula implies the second formula, but the second formula does not imply, does not imply the first one. Nothing surprising here, I hope. Perhaps the notation of it. Well, so the notation is just we have a logic S, some logical system, which is an extension of classical logic. This says that this formula needs to be valid. So this whole thing says in our logic S, it's valid that it's not the case that phi m psi, right? So phi m psi cannot both be true at the same time. Here it needs to be valid in the logical system as phi or psi. So at least one of the two needs to be true, right? And you can disable one or both of them. All right, so Aristotelian relations, then Aristotelian diagrams. The most famous one is, of course, the square of opposition. Right, we have four formulas, and we have a square. We have contrariety relation at the top, subcontrariety relation at the bottom. The diagonals are contradictory relations, and the arrows are subordination relations. And I've here used alpha, beta, gamma, and delta, but you can import any kind of formulas, right? If you have any normal modal logic that satisfies the T axiom, then box P, box not P, diamond not P, it also forms a square of opposition. Why? Because if we have, not the T axiom, even the D axiom is already enough. In any normal modal logic with the D axiom, these two formulas cannot be true at the same time, so you get a nice square. If you have a normal modal logic that does not validate the D axiom, then you get something like this, right? We have still the contradictory relations, but we don't have the contrariety, we don't have the subcontrariety, we don't have the subordination, because in a normal modal logic that does not satisfy the D axiom, these two formulas are not contrary to each other, and so these two formulas are not subcontrary, there's no subordination, etc. So what are Aristotelian diagrams? Aristotelian diagrams for me are any of these kind of diagrams that show these kind of relations. So it doesn't necessarily have to be the square of opposition. It can also be this, which we call the degenerate square of opposition. But it can also be an extension like this, the Sherwood-Chesovsky hexagon. It can be Jacobi Cessna-Larcher hexagon. There can be octagons. There can be anything. I'm interested in all of those diagrams. And I will be talking about those during this talk. So that's the general introduction. What are Aristotelian diagrams? What do I mean with Aristotelian diagrams? The second part of my title is about logic diagrams. So I'll also tell you what are logic diagrams. There's a whole tradition of people talking about logic diagrams. They all give slightly different definitions, but I'll use a definition by McAfee and Shin from their overview paper in 2012. They define a logic diagram as a logical system, so a logic, which has a list of transformation rules, a form of semantics, like any logic, but the thing that's different from a regular logic is that the vocabulary of a logic diagram is diagrammatic. So what is a logic diagram? A logic diagram is a logic, something with a form of semantics, something with rules to change the diagram, to change the well-formed formulas. But instead of having symbolic formulas, you have diagrams. So the well-formed formulas of your logic are going to be diagrams. And the elements of your language are going to be diagrammatic components. And I'll just give one example of what's studied in this tradition. So they'll, for example, say Euler diagrams are logic diagrams. Why? Because we can have a logic of these Euler diagrams where we can use some diagrams as premises, and then we have some rules, and with these rules we can infer another diagram, a conclusion. So, for example, here is the Barber syllogism in Euler diagrams. So we have one term is all A are B, right? All A things are contained within the set of all B things. We have a second premise, all B are C. All B things are contained within all C things. And then one of the rules of this logical diagrammatic system for Euler diagrams is if you have two figures like this with the same circle in each of the figures, then you can make a new figure. This one, so A is in B, right? And B is in C. So you just write them together and then you get a new diagram. And you can also, one of the other rules of this logic is you can remove a circle. So you can conclude from all A are B and all B are C that all A are C. Right? This is a logic diagram. Why is it a logic diagram? Because we have a real logic. We have a set of rules. We also have a form of semantics, the set theory. And we can make derivations in this logic. But the whole vocabulary of the logic is diagrammatic, right? We don't have formulas, we don't have conjunction symbols, that kind of stuff. Instead, the things that we are dealing with are diagrams, in this case, order diagrams. Okay, so far for logic diagrams. Now in my eyes, very strange thing is that in this tradition, there's a huge skepticism towards Aristotelian diagrams and towards the square of opposition. So, for example, Montaigne, from whom I got the definition of a logic diagram, they write, Aristotelian diagrams are not logic diagrams, but merely, and they literally use these words, illustrative diagrams, merely visual aids, not logic diagrams. But this tradition goes back much further, so even in 1967, the Queen says explicitly that the square of opposition is not a true logic diagram. And also more recently, for example, Jens Lemansky, yes, in 2018, he discusses 3 texts and then he mentions in passing, these 3 texts do not contain analytical logic diagrams in the strict sense, but rather some squares of opposition. So again, these squares of opposition are not considered logic diagrams in this tradition. And that's what I will challenge in this talk. So I will try to show that actually Aristotelian diagrams in square of opposition are logic diagrams, even by their definition. So why do I think so? Well, the basic intuition is you can use these Aristotelian diagrams for reasoning. If you see an Aristotelian diagram, then you can read off things, right? You can read off, oh, there's a contrariety here, and therefore there's a contrariety there. But even more importantly, I think where the reasoning happens is in constructing the diagrams. Right? When you start drawing a diagram, you have maybe 2 contradiction edges and some contrariety, and then you think, but if there's a contrariety here at the top, then I can conclude that there must be a sub-contrariety here at the bottom, and there must be 2 subalternation errors. Right? This is reasoning. This is coming to conclusions. And in this talk, I'll try to make that precise. So I'll present a logical system based on Aristotelian diagrams. So a logical system which, according to this definition of Montaigne and Shin, has a list of transformation rules, has a form of semantics, and has a diagrammatic vocabulary. Right? So the well-formed formulas of this logic will be Aristotelian diagrams. So first, going towards the language. I'll define a vocabulary. Very simply, a vocabulary consists of a set of formula constants, so like the size and size that we saw at the examples before. Then a number of lines, solid lines, dashed lines, and dotted lines. I could equally as well have said red, blue lines, and green lines. Doesn't really matter if you need to do something, so I'll do it in black and white for this presentation. And finally, arrows. Right, these 3 components are the 3 things from which Aristotelian diagrams are built. So I will use the formula variables from the beginning of the Greek alphabet, alpha, beta, gamma, as the meta variables ranging over the set C of formula constants. That's just some bookkeeping. And then, so a well-formed Aristotelian diagram, so the well-formed formulas of our logic, will be defined as follows. It's every non-zero but finite number of formula constants written on a page. Right? So if you just have some formulas written on a page, I already count that as an Aristotelian diagram. But also, if you connect any of these formulas with any of the things in the vocabulary, right? Any of the lines or the arrows, then we also get a logic diagram. Sorry, a well-formed Aristotelian diagram. So if D is a well-formed Aristotelian diagram which contains 2 formula constants alpha and beta, then the diagram obtained by connecting alpha and beta with either a solid, a dotted, or a dashed line, or an arrow is also a well-formed Aristotelian diagram. And finally, only diagrams obtained in this way are well-formed Aristotelian diagrams. So you might recognize this is very similar to the normal definition of well-formed formulas in logic, but now our well-formed formulas are diagrams instead of something more classical. Okay, so that's the language. let's give some examples. So all of these examples that we saw before are well-formed Aristotelian diagrams according to the definition, right? They're all a bunch of formula constants. In this case, the formula constants are just formulas. And then they are connected in some way with solid, dashed, dotted lines, or arrows. But maybe you might be a bit surprised. These are also well-formed Aristotelian diagrams according to my definition. And you might think there's something fishy going on, and I would agree with you if you think so. Why is there something fishy going on? For example, here from alpha to delta, there's both an arrow and a dashed line. And here there is nothing that's contradictory to this alpha.
It had the same meaning, these two dots or have the same meaning that the other dots or not.
So is the question whether these have the same meaning as this?
Well, that is for
This, yes. So these are supposed to be the same indeed.
this is used for universal statement.
Sorry?
This is used for universal statements, always, or propositions, or hard different meanings.
So the things and the vertices are supposed to be formulas of a language, but I abstract away from that and I use these alpha, beta, gamma, delta as variables to range over whatever concrete logical language you want to talk about. Does that answer the question?
Not exactly. To go back to the diagram that you presented before, you have different combinations. Yeah,
This one?
this.
Yeah, so here you have, well, if you just look at these four and the things that connect them, then you just have a spherical position. But we can extend it with more formulas. And then you can see there are also relations between these formulas. So for example, if we are working in modal logic KT, then this could be box P, this could be P, and this could be diamond P. Right? Because it's necessary that P implies that P is the case in KT. P implies that it's possible that P, but also it's necessary that P implies it's possible that P. And the diagonals, so here, well, if this is box P, then for example, this can be box not P, this can be diamond not P, and if this is P, then this can be not P, because then we have a contradiction between P and not P. But for example, also contrariety between here and here, because this was P and this was box not P, and it cannot be the case that it's necessary that not P, while P is also the case in normal logic. Right? Yes. So to go back. Yeah. So these are well-formed Aristotelian diagrams, but there's something strange with them, and I'll explain this later by saying, well, these are maybe well-formed, but they will contradict the axioms that I'll present. Another set of Aristotelian diagrams, according to my definition, are well-formed, but are strange, are these. And I'll call these unfinished diagrams. Right? We have all of the ingredients from our formal definition of language, but there's something missing. We know, for example, if there's an arrow here, then there must also be an arrow between these two. So that's why I call them unfinished, because there are still things that we can add, given just and only the information that we have. Right? It's just an aside to make the definition of the well-formed diagrams a bit more intuitive.
So, the definition of diagram,
Not necessarily. Yeah. So, even if there is no relation, I would still consider it a well-formed Aristotelian diagram, even if it's just the formulas. Then you can add whichever of the relations. So this is just, all right, when it's something Aristotelian diagram, this is just to exclude, for example, Euler diagrams with circles, they are not Aristotelian diagrams. But this is not yet saying anything about the interpretation of the Euler. Okay, So what I presented now is the last thing of the definition, a diagrammatic language, a diagrammatic vocabulary, right? Remember the definition of logic diagram was, it's a logical system which has transformation rules, formal semantics, and a diagrammatic vocabulary. So I said that the well-formed formulas of my language are well-formed Aristotelian diagrams. All these well-formed Aristotelian diagrams are diagrams. And the vocabulary consists of the components of these diagrams. So I would argue that this vocabulary is diagrammatic. So I've at least fulfilled the third requirement of the definition. This is, by the way, where one of my reviewers already had a problem. He wasn't convinced that this was a diagrammatic language. I don't see his point, but if anybody has thoughts, I would be happy to hear them as well.
How do you distinguish between diamond P and Q?
What do you mean? How do you distinguish the meaning of the?
The graphically in the diagram. How do you distinguish between diamond P and P?
So I would just have those as different formulas and diagrams. So the same way that I distinguish between box P and diamond P, I could also have written instead of diamond P here, for example, just P. Not P.
Only.
So just negation P.
Yes.
Yeah. So I could have rewritten this diagram and left the diamonds out here, and then you have a P and a not P.
This is one of the theorems specify model logic that possible P like P I implemented.
No, not possible P implies P, but P implies possible P, or box P implies P. That's the P action. So to go back, so I've argued that I have a diagrammatic language. So then I go to the axiomatization to deal with the requirements that we need to have transformation rules. So what does the axiomatization look like? First, I'll present some axioms. I don't actually know if the word axioms is the right term here, but again, if you have thoughts, I would be very happy to hear them. But first, for axioms. So within a given well-formed Aristotelian diagram, I say the first axiom is that for every alpha, there's no solid dashed or dotted line between alpha and itself, and also no arrow from alpha to alpha. So I exclude all diagrams that have arrows or lines from one vertex to itself. And between any two different alpha and beta, there's at most one line or arrow between them. For any alpha, beta, and gamma, if alpha and beta are different and there's a solid line between alpha and gamma, then there's no solid line between beta and gamma. So what this means is basically, well, there's only one formula in the diagram that's in contradiction with the other formula. Right? So you cannot have two, or you cannot have three formulas in the diagram such that there are two contradicting lines there. So there's at most one contradictory formula, and then the last axiom says there's at least one contradictory formula in the diagram. Alright, so these axioms, if we go back to these diagrams, you can see that these diagrams, though they are well formed according to my definition, they violate the axioms. Why? Well, for the first one, there is no formula that's in contradiction with this alpha. Here as well, there's no formula that's in contradiction with this alpha. Here, we violate that there is only allowed to be one connection between any two formulas. And here we have the case where delta is contradictory to two different formulas. Okay, those were the axioms, but the definition was asking for transformation rules. So we'll get to the transformation rules now. The first set of transformation rules are introduction rules, right? And the demand is apply the introduction rules only if the consequence of the introduction rule hasn't been fulfilled. So for every alpha, beta, gamma, and delta in a well-formed Aristotelian diagram, the first introduction rule is introduction of the dashed line. So if there is a solid line between alpha and beta and an arrow from gamma to beta, then you can draw a dashed line between alpha and gamma. Right, so we have, I'll illustrate these on a further slide, but I'll first go through all of the introduction rules. So we have introduction for the dashed line, then introduction for the dotted line. If there is a solid line between an alpha and a beta, a solid line between gamma and delta, and a dashed line between alpha and gamma. So think of an unfinished square of opposition with two diagonals that are contradictory, and we have a dashed line on the top. Then we can draw a dotted line between delta and beta, so we can draw a dotted line on the bottom. And introduction of the dotted line, then introduction of the arrow. If there is a solid line between alpha and beta and a dotted line between delta and beta, then we can draw an arrow from alpha to delta. So think, for example, of the top left corner of square of opposition. Right? If we have a formula here, then a dotted line to another formula here, a solid line to another formula here, then we can draw an arrow from this formula to this formula. And finally, we have a transitivity rule for the sub-alternations for the arrows. So if there's an arrow from alpha to beta and an arrow from beta to gamma, then you may draw an arrow from alpha to gamma. Okay, let me illustrate this. Okay. Before I illustrate it, there's expansive statement of Libet. If any of the axioms, remember that it's the four axioms, does not hold, then you're allowed to draw any well-formed Aristotelian diagram whatsoever. So if you're violated the axioms, then any other diagram follows. And finally, a weakening rule. So you are allowed to remove any dashed line, dotted line, or arrow from the diagram. And with all of these transformation rules, we can now define a consequence relation. The consequence relation is simply a diagram D follows from a diagram D prime, and we write it like this, right? D prime syntactically implies D. If and only if this diagram D can be obtained by applying a finite number of transformation rules to D prime, right? And the transformation rules are the introduction rules or the structural rules. There's a small typo. So this was all the theory. Let me make it a bit more precise. So let's say we start with this unfinished diagram. Right? We have two contradictories, two solid lines, and an arrow, sub-alternation. We can use an introduction rule to draw this diagram. Right? The introduction rule for the dashed line says if you have an arrow and a solid line, then you're allowed to draw a dashed line here. Right? So the introduction of the dashed line. And from there, we can also draw a dotted line, because the introduction rule for the dotted line says, well, if we have a dashed line between two formulas, and we have the contradictories of those two formulas, then you're allowed to draw the dotted line. And finally, to finish the square of opposition, we are also allowed to draw an arrow here by the rule arrow introduction. So you see from just this premise, we can derive this and this and this. So from one well-formed Aristotelian diagram, we are allowed to syntactically derive any of these well-formed Aristotelian diagrams. So I talked before about finished and unfinished diagrams. So let me give now a precise definition. A finished diagram is any diagram where we cannot apply any more introduction rules. Right, so this is a finished diagram, whereas these three on top are unfinished diagrams. This distinction plays a role in the completeness proof, but it's also, I think, very intuitive. Right? If you read the text, you'll most of the time only see finished diagrams. But when I instruct my students, when I explain to them how a square of opposition works and give them exercises, I also give them an unfinished diagram and tell them, please finish this diagram for me to show that you have understood. I think originally I had to do like 1 or 2, but okay, yeah, because we started a bit later. That's good. So there are also the 2 structural rules. Let me just illustrate weakening for a second. Thank you. So weakening simply says you're allowed to remove any of the lines, or sorry, the dotted or dashed lines or the arrows. So from square D, we can go to square E. And this also means that we can come up with derived rules, right? Because from this square D, we can get to here. And we saw on the previous slide that from this square A, we could get to this square B. So if we link up all of these different derivations, then it means you can get from this square A to this square E here. So we have also a derived rule, a sort of contraposition rule, that we can get from the square without this arrow to simply the square with this arrow. All right, so this was the axiomatization, and this neatly fits within this definition of what a logic diagram is, right? A logic diagram was a logical system which has, as one of the things, a list of transformation rules, and indeed, I've given a list of transformation rules, namely the introduction rules and the structural rules. These transform the diagram into a new diagram. Very much in the same way as we did for the Euler diagrams, right? With the Euler diagrams, if you remember, we had the diagram with 3 circles, and then we turned it into the diagram with only 2 circles. Right? That was one of the transformation rules for Euler diagrams. If there are no questions there, then I'll go to the third component, namely the semantics. So I have to define a model. What's a model? Well, a model for this logic is a triple consisting of an F, S, and an I, where S is a logical system that has a language which I will call LFS. This language must have Boolean operators and a model of theoretic semantics written like this. This just basically means I'm only interested in this talk in logics that are extensions of classical logic. Right? I want Boolean operators. If you don't have that, then you lose some of the axioms and some of the transformation rules, which is very interesting to think about, but I won't go into that right now. So indeed, S is a logical system. Then I is an interpretation function that interprets all of the formula constants that assigns to each formula constant a formula of the language of your logic S. This is an injective function. And finally, F is a fragment of our logical language, such that for every phi in this fragment, there is another psi in this fragment, such that psi is equivalent to the negation of phi. In other words, for every formula in our fragment, there must be another formula in the fragment that is contradictory to this original formula. Secondly, for every phi in the fragment, there is not a psi, a different psi, such that this psi is equivalent to the original phi. So our fragment does not contain any formulas that are equivalent to each other. And finally, there is no phi in the fragment that is a tautology or a contradiction. Right? There's no phi that is valid on itself or whose negation is valid. These are some requirements that we often see, well, in the study of logical geometry, but also that almost all of the diagrams, at least almost all of the diagrams for classical logics satisfy. So this is a model. Then, of course, next to a model, we need some semantic classes, some way of interpreting our formulas. In this case, our well-formed formulas are the diagrams on a model. So let M be a model. This is the scribble. Then M satisfies an Aristotelian diagram B, if and only if all of the following conditions are met. And these conditions are as follows. So for every alpha according to B, for every formula constant that you see in the diagram, the interpretation of alpha is an element of the fragment of our model. And for every alpha and beta occurring in the diagram, such that alpha and beta are connected by a solid line, it must be the case that our logic S says that the interpretation of alpha is contradictory to the interpretation of beta. So you see, this is really semantics. Here we're gonna not just be talking about things like solid lines, dashed lines. We're gonna be talking about what solid lines and dashed lines mean. And then the next few ones are very similar to the second rule. So for every an alpha and beta occurring in the diagram that are connected by a dashed line, their interpretations need to be contrary to each other. For every alpha and beta connected by a dotted line, their interpretations need to be subcontrary to each other. And finally, if there is an arrow from alpha to beta, then the interpretation of alpha is in subordination with the interpretation of beta. Okay, and then so we have models, we have semantic classes, then we can define a semantic consequence relation. So a well-formed Aristotelian diagram D is a semantic consequence of a diagram D prime, which we write like this. If and only if every model that satisfies D prime also satisfies D. So let me very briefly say something about soundness and completeness. Soundness is very straightforward. It just suffices to check that all of the transformation rules are valid. And given the ease of the semantics, it's very easy to do this. Yeah, this is, I mean, also nothing new. It's just known results from the literature now phrased a bit differently as a soundness result instead of as a result about Aristotelian diagrams. Completeness is a bit more involved, but definitely not impossible. So I have a paper with known as an I 2023. It's called The Modal Logic of Aristotelian Diagrams. And there we prove that we know all the structural properties of these Aristotelian diagrams. And you can also show that the rules I presented here capture all of these structural properties. So that's an argument why the logic would be complete. I won't go through the whole completeness proof. Let me just briefly say that this paper also gives you a recipe that if you have an Aristotelian diagram, then it says, all right, from this Aristotelian diagram, you can always give a logic and a fragment of language of that logic that will make this Aristotelian diagram meaningful. So if we have just a diagram, right, just some formulas with solid lines, dashed lines, arrows between them, then we can, with this recipe, give a logic and a fragment that would give that diagram, and we can use this recipe to construct phenomenal models. And with this phenomenal model construction, we can prove completeness. I won't go into the details. It's a bit long and a bit boring for a presentation. But it's nice to see that the system is sounding complete. So to go back to the definition of logic diagrams, we have presented a logical system, which, as we have seen in this section, has a form of semantics. Right, so we have all three of the requirements of a logic diagram. So Aristotelian diagrams, according to Lee, are logic diagrams, right? We can give this logical system, which has a list of transformation rules, has a form of semantics, and has a diagrammatic vocabulary. So I would say that the people in this tradition of logic diagrams are wrong to discount Aristotelian diagrams, are wrong to discount this kind of opposition as a real logic diagram. I think it is a real logic diagram. But then, okay, this is not just a purely theoretical exercise saying, you're wrong. I think this also has some value on its own, right? Reasoning is one of the canonical uses of logic, or at least checking whether reasoning is valid or not. And I think you can do that also with this logical system. So, as I said in the beginning, my intuition is we actually do reason with Aristotelian diagrams, especially when we construct the diagrams. And this reasoning can be made precise with this logical system. So 2 examples, I already gave the kind of contraposition like example before. right? If we have a sub-alternation arrow, and then we have the contradictories of those two things that were in sub-alternation, then we can draw a sub-alternation between those two contradictories as well. So we can deduce from the premises that there is a sub-alternation and there are two contradictories that there is a second sub-alternation. Let me give another example for the modal logic S5. And I think this will also answer your questions, because here we have the Filosofía hexagon that I was talking about. So box P is necessary that P, just P, and diamond P, it's possible that P. And suppose that by the T axiom, we know that from box P we can derive P, and from the P itself we can derive diamond P, right? If it's necessary that P, then P will be the case, and if P is the case, then it's possible that P is the case. Given this information, we can use the transitivity rule to derive this subalternation arrow, right? So we can derive that from box P follows diamond P. There is a subalternation between box P and diamond P. And this is a reasoning step. I admit a very simple reasoning step, but it is a reasoning step that you can do with Aristotelian diagrams, and that is very useful. Maybe not for the modal logician that has already made 20 completeness proofs, but it's definitely useful for the student that's just learning about modal logic, right? That doesn't immediately see, in S5 from box P diamond P follows. But of course, this is not the only thing you can do, right? You can complete the whole diagram just using all of the introduction rules. I won't go through all of them, but here you can see it. So I do think this is more than just a theoretical exercise, as I said, to prove these people wrong. I think it's eventually done. All right, then going to the conclusion. So what have we done? Well, I've shown that there is some kind of prejudice against Aristotelian diagrams in the literature on logic diagrams. They just saw Aristotelian diagrams as illustrative, as not real, true analytic logical diagrams. And I have argued that Aristotelian diagrams actually are logic diagrams. How have I argued that? Well, I've set up this logical system that satisfies all of the requirements that people in this literature have for logic diagrams, right? We have a list of transformation rules that falls in the instrumentalization. We have a formal semantics, and we have a diagrammatic vocabulary. So, to come back to the question that was on the very first slide of this presentation, why are Aristotelian diagrams so ubiquitous? As you might remember, my co-author Atal is really interested in this question, and I think this gives a partial answer to that question. Why are Aristotelian diagrams so ubiquitous? It's a very difficult word. Because they are tools for reasoning, right? It's very easy, a very visual way of doing elementary reasoning in logic. And importantly, you need to not know anything about the underlying logic. So if you think back to the semantics, we always have an underlying logic. I call it S there. And you can make reasoning steps about your logic. You can make derivations about formulas in that logic without knowing the exact details of the logic. And I think that makes Aristotelian diagrams especially interesting for students who are just learning a new logic. And I think that might explain why we see these kind of diagrams so often in introductory textbooks. But it also makes them very useful for describing or thinking about very complex logics. And I think that might explain in part why we see these diagrams often in research papers where a very new logic is introduced. Then it might be illustrated by logic diagrams. Why? Well, even for people who have a hard time grasping the exact finesse of the logic, they can get some intuitive grasp of it. They can see, oh, these are the relations between the formulas. And this is some derivations that I can make about these formulas. There's also some possibilities for future work. If you've noticed, each time I was talking about a consequence in this presentation, I was just talking about one diagram being a consequence of another diagram. But we might also be interested in having two different diagrams as premises and then combining them into a new diagram. We still have to figure out how that would work exactly. Similarly, we might want to add new formulas to a diagram. Again, there's no room for that in the system I presented here, but it would be interesting to look at that. The completeness proof, I have a completeness proof, but I hope I can write it out in a bit. It's like 5 pages now, a bit shorter, a bit more precise. And finally, there is this whole literature on logic diagrams where these other logic diagrams, order diagrams, Venn diagrams, etc., are used for reasoning, and it would be interesting to compare these Aristotelian logic diagrams with that. That was it for me. Thank you very much for your attention.
Thank you. So we have some questions. Just questions, yeah? So,
have you considered great? Have you considered graded versions of diagram? Graded version will have vertices and edges annotated by quantitative variables, categorical variables, or continuous variables expressing degree of belief or strength of relations. That would be a nice extension of this formalism.
So, so the question is, so then like the solid lines and the dashed lines would be made more precise. They would have some kind of qualification.
Would have an annotation. An annotation would be a variable, say a real variable, expressing the strength of the relation, or in the vertex, the degree in which the statement is true. And all these applications to be reasoning systems, fuzzy logic, or statistics.
Yeah, that would definitely be interesting. So I haven't looked at that yet, but if you know some references, I would definitely be curious to look at it. No, thanks.
so
How can you express computer visions? I remember, for example, the rule or the God existence of 1979, I think, and you would say this line suggestion that possible up and down. And this is not represented in the diagram because it is not valid. It is not valid to go from possible. Okay? Peak to peak. It's not valid. But this is the heart of the proof of the thing. How can you represent complex? Because I remember that this proof contains about 20, 23 different steps in the deductive steps. When text was applied, how can you represent these very complex demonstrations? It is tricky. I think that the demonstration is tricky, but I think that you can represent complex reasoning how to keep the intuitiveness.
So I think the problem for that, so I don't think I can do that kind of reasoning with these kind of diagrams or with this logical system. Why not? Because my formulas, my diagrams, will only say something about the relation between formulas. So I can never have as a conclusion God exists. I can only have as a conclusion maybe something like God exists is contrary to God does not exist, or something like that. Okay. So no, I won't be able to capture that easily.
that is good.
Yeah, well, I don't know if I'm right before I'm asking the question, but when you introduce an annotation of the positions and formulas, you have, I think, you have to change in some way the definition of the context and lines and so on. Because with an annotated proposition, that relationship will change in degree. So, well, my question is a bit technical, I think, but in this S system, can be any system, even a non-normal model system or a non-classical system?
So it's not a non-classical system. So it can be a non-normal model logic, for example, but it needs to be an extension of classical logic because it needs to have the Boolean connectives. So a classical disjunction, a classical conjunction. If you go to non-classical logic, that's also something that you tend to look at because then it gets really interesting, right? So you're gonna lose some of the axioms, you're gonna lose some of the rules. Yeah, for example, if you go to like first degree entailment, you will lose introduction of the dotted arrows, dotted line, introduction of the dashed line, but you'll still have, I think, the category rule, for example.
Yeah.
So that's definitely something that's interesting to look at, but I haven't looked at it details yet.
Yeah.
But sorry, I interrupted you.
Thank you.
Yes, I would like myself to make some comments. I think the terminology, logic diagrams, as defined by Stef, it's a terminology which is quite obvious. I mean, the name, what it is here. Because what they have in mind is a system result based on diagram, like first, graph or Gonzalo. And then she herself, she developed a lot of system of reasoning based on diagram. So that's why I think the expression is not so good, but they should suppose that we need a system of logic, diagram logic system, something like that. Now, what you say well, but I think it's different to say well. When we are building some diagram, we are following a system. But this system is to build diagram. It's not. Yeah, it's not to describe reason. So I think this is two different directions. But then at the end of the talk, you say, well, we can also use, I think it's interesting. We can do that. We can also use the diagram to resolve. There are different perspectives of that.
So yeah, I fully agree with your first comments that like the terminology. Thank you. My back. Yeah, so I fully agree that the terminology is very strange, right? Because a logic diagram, what would that be? What intuitively, what did you think? It's a diagram about logic, right? Not necessarily a logical system. So something like, say, diagrammatical logical system makes way more sense. I fully agree. But yeah, logic diagram is the terminology they use. That's why that's using it. Then the second question about the reasoning. So I think, I don't know if this answers your question or if I'm just repeating myself, but I think that in constructing the diagrams, we actually do reasoning and we make reasoning steps. So in constructing the diagrams, there's two things that we can do, right? Once we've started the diagram, we can either look back at our original logic and see, all right, I have these two formulas in my diagram, and if I interpret these in the original logic, then I see, there must be a subordination relation between those. And that would be, in my terminology, going back to the semantics. But the other thing we can do is if we started drawing a diagram and we already have a subordination somewhere, we can see, oh, that means that there must be a subordination here as well, contrariety here and subcontrariety there. And I can do that without having to go back to the original logic, to the underlying logic. And I think that's a kind of reasoning steps that we are making and that I can capture with this system. So in that sense, I think we do reasoning with scarcity diagrams. But I don't know if that's an answer to the question.
No, I agree. I mean, we are reasoning with when we have a diagram that have different aspects. You are reasoning to build a diagram, and you are also reasoning to discover something else. So the two things are mixed, and I think that's why. More questions? Yeah, please.
Hello, Stef. Thanks for the talk. My question is about future work. So combining diagrams, I was already thinking about that when you did the presentation. Like it would be nice to have a lot of premises and then use all of them to deduce another diagram. And it seems to me that there's an obvious candidate, like with the Euler diagrams, you have circles that have the same name, so you identify both of them. Would that be the same thing here?
Yeah, that's definitely the direction that I'm looking at. That's definitely the direction that I'm looking at, right? Because if you have two, let's say, squares of opposition which share a formula constant, then you should be able to combine them into some kind of hexagon, probably. And yeah, that makes sense to me. I haven't worked out the details yet, so I don't know what you will get for new kinds of rules, transformation rules. But and I also don't know, maybe there might be other ways to combine diagrams as well. But yeah, definitely.
More questions?
I have this curious. Yes. You can go from the diagrams to constructing the logical systems. And how can you distinguish between A theory and A as action when you build the diagram? I don't know if it's because in many cases you can, if you use say some formula, you cannot deduce all the theorems that you want to do. You have to select very carefully the actions. Is there some procedure to select that way to get actions or theorems?
So I can interpret your question in two ways. So if you're talking about like the underlying logic, the theorems or the actions of the underlying logic, then I would say my system cannot distinguish between those. Right? I cannot say this is a theorem of the underlying logic and this is an action of the underlying logic. If you're talking about the logic diagram, right, the system that I presented today, to distinguish between theorems and axioms, I mean, I've given this list of transformation rules, but the transformation rules could also have been different, right? Instead of I now introduced the dotted lines given a dashed line and two contradictories, but I could also have done the opposite, right? I could have introduced dashed lines from dotted line and two contradictories, and then change some of the other rules as well. And these things are now derived rules, but they could have been my rules or my axioms, and you would end up with the same, let's say, theorems, the same tautologies of the system.
My question is, if you want to obtain a model logical system from the diagram, if you can infer axioms from the diagrams to the new system, not the axiom that you before.
I don't think you will ever be able to, because the diagrams are always going to be finite. So you're at most going to see like a finite number of relations between formulas, whereas an axiom scheme is about an infinite number of logics, an infinite number of formulas which are going to be valid instantiations of the axiom scheme. So the diagram will never be able to tell you something about the axioms of the underlying logic.
Okay. All right, any more questions? If not, thank you again.
Let's go to lunch somewhere, maybe some nice, and then we start again at 2:30.